Three, two, one, let's go. I'm excited because we're talking about my favorite object in mathematics, the series, and we're going to talk about how we can use them to my favorite class, differential equations. So let's go. All right, so let's recall that any constant coefficient in linear differential equation, homogeneous in this case, we know how to solve, right? Y double prime minus 4y, go to the auxiliary equation, r squared minus 4, set it equal to 0, r is plus or minus 2, e to the 2t, e to the negative 2t, we got our independent solutions, boom, done. Right, and in fact we didn't even need that because, if we added the 4y over, then I'm asking you find the function so that y double prime equals 4y, well, my exponentials clearly satisfy that. So for constant coefficients, you can always go to the auxiliary equation and get roots. There are some ins, some outs, and what have yous, depending on repeated roots, complex roots, and all that other fun stuff we talked about. But for the most part, it goes pretty well. Now, what happens if we replace the constant with a variable, with a function that depends on the independent variable? Well, it turns out that even the most reasonable variable coefficient differential equations can be incredibly challenging to solve. Now, we saw the Cauchy Euler equations, which are kind of rigged to just work, basically. So this differential equation is just a minor modification of the one we just talked about that we can easily solve. I've replaced the constant 4 with the variable x. And even this, as simple as it is, requires a very careful study. So it turns out that the solutions to these are things called the Airy functions, which are part of a broader class which are called special functions. Special functions is like this branch of math where they didn't really have like a good name for it other than, hey, we're looking at functions that show up in differential equations and physical applications, and they're not easy. They're not like stuff like sine or cosine or exponentials or logarithms. They're these other animals, right? So the Airy functions, like just as a description of them, they're the functions whose second derivative is themselves times the function x. It's a very easy description. But it turns out that they're very complicated functions, as we're going to see. So, speaking of special functions, it's an exciting branch of mathematics, and if you go to the Wikipedia page for it, they list off, it's a weird Wikipedia page, because they have like a section of like people that do special functions, which other branches of math usually don't have that, just a little section of like, here are people. So Iowa State makes an appearance because one of the people who are listed as a researcher of special functions is Professor James Wilson, who's retired. He was the director of undergraduate studies before I was. And he's actually known in the world of special functions because he cooked up a special type of polynomial that are now known as the Wilson polynomials. So we at Iowa State, we got a little connection to special functions, that's neat. But anyway, so these are known, but how do you get them? How do you handle them? So in general, variable coefficient FEQs, there's a lot of different methods of getting to them. Today we're going to talk about the method of using infinite series. So let's remind ourselves what a series is. So that's the symbology we use. And what is it? Well, the infinity sign should be triggering dreams of calculus, right? Because it means that a limit is going down, and specifically, it's the limit of the sequence of partial sums. So we have a collection of numbers, x1, x2, x3, so on and so forth. And what we do is we add them up, term by term, and we look at that. So we look at the first partial sum, the second partial sum, the third partial sum, so on and so forth, and then we take the limit. So in other words, this is representing a limit of summations. This symbol right here does not actually perform a summation. It performs a limit. It's very important. to remind yourself of that. This thing on the left is not handled by doing additions. You do limits to deal with this, right? And that, right, and sort of, this is one of those cases where the symbols used can like lead to bad intuition. A very famous example is what's the infinite sum of 1 minus 1 plus 1 minus 1 plus 1 minus 1. Initially, it looks like everything cancels and you get 0. But if you start goofing with it, you start getting more bizarre values. But if you look at the limits oscillate between 1 and 0, so it doesn't converge. Despite what a bunch of ding-dongs from the University of Nottingham would have you believe. It's not equal to 1/2. Do not come at me with that. Alright, so speaking of 1/2, let's talk about a particularly famous classic example. If you keep adding up powers of 1/2, so if you do a half, plus a fourth, plus an eighth, plus a 16th, plus a 32nd, plus a 64th, plus a 128th, plus a 256th, there you go. 256 is a good place to stop. I don't feel like multiplying that number by 2 in my head. What is it, like 14? No, 412. That's what it is. 4, 5, 20. Why am I even talking? Jeez. Just revealing that I don't know how to add and multiply. The hack fraudery, man. Top tier. Anyway, so this is a very classic example. You definitely ran afoul of this in calculus, and it's pretty easy to convince yourself it's true. Just think about traveling a distance of 1, and you're halving your distance every step. So you start at 0, and then you move to a half, and then you add a fourth, so you're now at 3/4. So 1 minus a 1 over 2 to the 2 power, the second step. Right, and you keep doing it, you keep halving, and right, you keep removing more and more and more until, right, you get as close to 1 as you want. So when you take the limit, you get that that's equal to 1, right? And this specific summation is actually a special case of the geometric ones. Right, so if you don't fully believe this formula there, well, it's a geometric series trick. Now note that this starts at 0 and this one starts at 1. It really doesn't matter. It's starting at 0, so you just got a nice formula on the right-hand side. If we started at 1, it's a little uglier. It really ultimately does not matter where we start series. Start at -12, whatever, it doesn't matter. But, we like to keep things nice and clean, so we usually start at 0, we start at 1. Occasionally we need to start at 2, but that's about it. Alright, now note here, the geometric series, given a number x strictly between -1 and 1, we have this. So for each x, I can compute a series. So I can make a function, and these are known as power series. So one way of viewing a power series, so here I wrote this out on the right-hand side, which is another way of writing an infinite series. When we write it this way, you can really see that it's basically saying that it's a polynomial that's infinitely long. And indeed, polynomials are basically a special case of the power series. So as we just saw, though, polynomials are defined everywhere. However, power series are not necessarily defined everywhere. That's something to keep in mind, especially for, for example, the most basic power series, you replace all the coefficients with 1. This is actually only defined from -1 to 1. In general, power series are only defined on an interval. Sometimes they're defined for all real numbers, though. And sometimes they're only defined at 0, where they take C0 as their value. So, speaking of being defined in all real numbers, before we jump into using these to solve differential equations, it's good to remind ourselves of some power series that hopefully we remember from Calc 2. Without a doubt, the most essential and important one is this formula for e to the x. It's probably no understatement to say that this is the most important function in mathematics. It's certainly the most important function for differential equations, as we've basically been using e to the x to sort of build up and create solutions. Sine and cosine also have power series, and the first thing you should recognize is, hey, that looks like the even terms of e to the x, and this looks like the odd terms of e to the x. Now, there's this -1 nonsense. How do we deal with that? Well, if you plug I in, replace x with I to the x, so pull apart the even and the odd terms, even powers of I are going to give you -1. Odd powers are just going to give you I times -1 because of the plus 1 there. And oh, look, boom, there is another proof of Euler's formula using power series. Nice. Yeah, so once people started getting working on power series, and these formulas were known, I believe that I'm pretty sure Newton had these more or less figured out. The second this was discovered, right, it's very natural to plug I in. Although even by Newton's time, I think the imaginary numbers were still kind of like poo-pooed. They were like, they're nonsense. The 1700s was really when they had they started really taking hold as an important and essential tool in mathematics. All right. Anyway, let's talk about solving diffie-Q. So let's revisit this differential equation. So we talked about it having solutions, right? We know it has to have solutions, two linearly independent ones, known as the Airy functions. Well, how do we get them? Well, we can use differential, obviously we use differential equations. We can use infinite series to get them. So, just like we had done before, where we were like, well, let's guess an exponential works and plug it in and get the auxiliary equation, let's plug a power series in and figure out what needs to go on. So now note that the goal here is to figure out what the coefficients need to be doing. So my hope is that I'll be able to get some formulas for that. Now, if I can get nice, clean, explicit formulas for what all the coefficients need to be, that would be great. But as we're going to see, sometimes you work with what you get. Alright, so we need to plug this into the differential equations. That means I have to take two derivatives, and derivatives of these are exactly how you think they should go. Right? It's a polynomial. When you take a derivative, you just take the derivative. Just start from the left and go to the right. There's a limit going on. There's some technical conditions about when power series can be differentiated and other junk, whatever. We don't need to worry about that. We're allowed to take the derivatives, and their derivatives are what you want them to be. These things right here. Alright, so we take the derivatives. It goes the way you want it to. Just, again, think of them as infinitely long polynomials. Okay. Now, if I want to solve the differential equation, that means I need to plug this thing in for the second derivative, plug this in for the function itself, and try to do something with the coefficients. So let's do that. Okay, so if we plug them in, it looks like this. Now, note what I did here. Here we've got these, wrote those out. Here I got those, wrote them out. Now, the 2c is just going to be on its own. There's no constant term from the subtraction that's going to show up. There is an x term, though, c naught x. That's going to subtract 6c3x, so we can factor the x out and get 6c3 minus c naught. So note that y double prime minus 2i, we're actually rewriting it as a power series in its own rights, where we're collecting the x squared, the x cubed, so on and so forth, and looking at what's going on. Now, the constant term doesn't seem to be following any sort of pattern, but the term for x, the term for x squared, we see something. We see this pattern specifically emerging, right? Well, you'll have 2n times n plus 1, which is what's happening over here from the n plus n minus 1. Note that I've shifted it to make it match. And it'll be subtracting cn minus 1, where x to the n is right there. So how did I get this particular formula right here? Well, I looked at the pattern. Another way of doing this was to bring the x in here, change this to an x to the n plus 1, re-index this series so that you can combine the two, and then pull it apart, and yeah, your textbook works out the details on that, and if you want to, get really good at manipulating series like that, go ahead. I think it's a little bit better to just write it out as polynomials, write out more terms if you want to see more terms, but usually when you do plug in an infinite series to solve the diffie-Q, the constant term and maybe the term associated with x just do something weird, and then the other ones follow a very clear, distinct pattern. Alright, so remember, this was y double prime minus xy equal to 0, so we're going to set this equal to 0 now, which is this. Now, remember, a power series is like an infinitely long polynomial. If a polynomial is equal to 0, that means the coefficients have to be 0. Same is true for a power series. If a power series is equal to 0, all of its coefficients must equal 0. All right, so that means I know that 2 times C2 has to be 0, and all the other terms, which we noted are of this form, for n greater than or equal to 1, those must all equal 0. All right, so very similar to how we dealt, with like partial fractions or something, where you get your polynomials, set them equal to 0, coefficients got to be equal to 0. Same thing is true here. Now, this first one, that just tells me that C2 has to be 0. This one right here, though, gives me a lot more information, and this is a lot more important. So this is something that always happens when you plug a series into a differential equation to solve it. You get this, which we call the recurrence relation. So, like I said earlier, when it comes to plugging in a power series to solve a DiffEq, the goal is to figure out some sort of formula for the coefficients. Sometimes you luck out and you get a beautifully nice and explicit formula that tells you that this is what each C sub n needs to equal to in terms of n. Other times you get this. You get a recurrence relation. So you get a way of telling you how to generate the next coefficient based off of previous ones. So what we have to do now is basically go, all right, let's start with some coefficients and then see where we go. Okay. So specifically, what we're going to be able to do, using the recurrence relation and the fact that I know that C2 has to be 0, I actually will be able to tell you what C sub n needs to equal based off of C0 and C1. So typically this is what you do when you want to actually figure out what are the series of these functions. Okay, so we'll treat C0 and C1 as just parameters. They're some unknown numbers. If I have initial conditions, I can figure them out, but we'll leave it as is. So, like we already pointed out, we know that C2 is 0. And now a whole bunch of stuff's going to go up on the screen in a moment here, but let's break it down. If I want to compute what C3 is, I now just use the recurrence relation. Right, C3, that corresponds to 2 plus 1. So that means I have a C sub 2 here. And then I have n plus 1. Right. And so I've got my 3 times 2. So note here, I'm just going to pull the C0 out, and then I'm going to have this fraction that shows up. Do the same thing for C4, and now at this point, each one of these numbers are just going to increment up by 1, because we're incrementing up each subscript by 1. Okay, so C4 will just be C1 times 1 over 4 times 3. I'm leaving it multiplied out. If you want the actual concrete numbers, go ahead. Now, C5, we see something interesting happen, because C5 is going to be based off of C2, right? It's a recurrence relation. It's telling me how to get to the next term based on the previous ones. Well, C2 is 0, so that means C5 is 0. And if we skip ahead, C8 will have to be 0. C11 will have to be 0. C14 is going to have to be 0, and so on and so forth. And now that I know what C3 is, I can tell you what C6 needs to be, because just plug in what we know for C3, that gives me this formula for C6 in terms of C0, and then you can plug that in for C9, and so on and so forth. You do it for C12, C15, yada, yada, yada. And similarly for C7, we know what C4 is equal to in terms of C1, so we can solve for that. And then given that, we can solve for C10, then C13, C16, so on and so forth. Right. So it's worth noting that you can actually sort of come up with an explicit formula here. Note the bottom is a factorial, but it's missing a couple of terms. So if you want to, you can rewrite these as factorials and then put the missing terms in the top. So there's sort of like an explicit formula you can come up with, but usually we're not super interested in those. So it's worth noting, if you actually do look up the array functions, they do have, the coefficients do have explicit formulas, but they involve the gamma function, and bleh, let's not get too off the deep end there. But anyway, now that we have this and we see a nice little pattern, I can give you a pretty reasonable solution to the differential equation. You can solve it finding this power series. I have a recurrence relation for my coefficients, so I can tell you how to get them. I have a compact formula that tells me what to do, and if I look at all the terms that involve C0 and I look at all the terms that involve C1, it actually gives me a general solution. So note here, C0 associated with the constant function 1. Minor typo right there. C1 is associated with x. Let me fix that. That's a copy pasta accident right there. Okay. Right, so you can think of this as x naught, which is attached to c naught. C1 is attached to x, right? And then all the other coefficients, we know that x squared, since that's attached to c2, right? Just follow the pattern, that's 0, so it's gone. x3, c3 was dependent on c naught. C6, formula for that in terms of C naught. C9, we had a formula for that in terms of C naught. Same thing with C1. C1 is the one attached to X. C4 was in terms of C1. C7 in terms of C1. C10, so on and so forth. And usually when you're cooking up power series solutions for diffie-qs, you only need to write off like the first 10 terms and basically go like, yeah, you can see the pattern. It's fine. I have the recurrence relation. If you really want to generate more, go ahead. And like I said, there are kind of ways of getting closed form solutions, but a lot of times they're not worth it. Something like this is the best you can do. All right. And there you go. That's how you use power series to solve differential equations. So I did a second order one. You'll have some fun with some first orders and some other second orders. And yeah, good stuff. All right, and it's worth noting that this is really just kind of scratching the surface. You can use other types of series. So not only do power series do a pretty good job, but you may have heard of something called Fourier series. And oh boy, yeah. All right, well, that's it for today. Hope you liked it. See you next time.